Okay, so let's start. In the last class, in the last few classes, we looked at the following class of optimization problems. It's general class of optimization problems that could be stated as one of minimizing a function f0 of x subject to a bunch of inequality and equality constraints. And we saw a procedure in order to minimize this and the notion of a dual optimization problem. So given any optimization problem, you can always frame the dual optimization problem. And we saw that irrespective of what properties the original optimization problem satisfies, the dual optimization is always convex. So it's one of maximizing a concave function subject to some constraints, which was nice. And we saw a couple of examples to see that even though the original optimization problem, constraint optimization problem, was a bit complicated, you could in fact obtain solutions or efficiently obtain solutions for the dual optimization problem, and hence get the solution to the original optimization problem. And the way to do this was using these so-called KKT conditions. So solving the optimization problem was reduced to one of solving for a bunch of equations, and if we are able to solve for those equations, then we are done. But all of this rested on some properties, and we saw that the KKT conditions in some cases can be necessary, in some cases can be sufficient, in some cases both necessary and sufficient. And in particular, if the optimization problem is convex, which means that f0, f1 up to fm are all convex functions, and h1 through hp are all affine functions. In this specific case, the KKT conditions turn out to be sufficient, right? So you can always solve for the KKT conditions, and if you get a solution, then you're done. Okay, but in order to do that, we need to know whether a given problem is convex. Correct. So you're posed with some optimization problem. First things to verify is whether this is a convex optimization problem. Or given a physical problem, you want to frame this as a convex optimization problem. So in the next few classes, we'll see, of course, we've defined a convex function previously, but apart from the basic definition, we didn't explore that any further. So in the next few classes, we'll explore that in more detail. We'll see how to verify whether a given function is convex and how to generate convex functions from simpler convex functions, similar to what we did for convex sets, right? And we'll see that this notion of convexity is fairly general. It can be generalized in many different ways. One way that we saw was using generalized inequalities. If you have a generalized inequality, then you can define a notion of convexity in terms of those generalized inequalities. So a large part of this theory that we're developing over here holds not just for functions, real valued functions, but can also hold for vector valued functions and more complicated functions. Okay. So let's go back to our definition of a convex function. Right. So when did we say that a function is convex? Suppose we are given a function defined over some vector space. In general, we are going to consider R to the n, but for example, it could also be the space of say symmetric matrices and so on. So all of these are finite dimensional vector spaces that we're considering over here. So given a real valued function, we say that this is convex if for all x1, x2 in the domain of f. So this is the region where f is defined. We have f of alpha x1 plus 1 minus alpha x2 is less than or equal to alpha times f of x1 plus 1 minus alpha f of x2, and this holds for all alpha between 0 and 1. which one we can say, but we also want a slightly more general condition wherein f could potentially be defined only on a subset of V. So it could be that the domain of f is some subset of V, but we'll see that that doesn't really matter in just one step. I'll show that even if the domain is a strict subset of V, we can sort of modify f just by a little bit to ensure that f is convex throughout over all of V. Okay, now suppose that the domain is indeed in fact not equal to V, right? So we can define this new function f tilde of x. Let us define this to be equal to, so for all points in the domain, this is exactly equal to f of x. And it's equal to plus infinity otherwise. Okay, my claim is that even though f is defined only in a small subset, f tilde is in fact going to be convex. Do you see why that is the case? So for if you take any x1, x2 within the domain, then obviously f tilde satisfies the property of a convex function. So there's no question about that. The only thing that you have to wonder about is what happens when either x1 or x2 does not lie in the domain of f. So suppose, let's say x1 does not lie in the domain of f. Okay, if both x1 and x2 are outside the domain, then anyway both the left hand side and the right hand side would be infinity, because any convex combination would also, so the right hand side would definitely be infinity. So even otherwise, let's suppose that x1 is not in the domain of f without loss of generality. Then what happens to the right hand side? Have alpha times f of, let's say the RHS would be equal to alpha times f tilde of x1. We want to verify that f tilde is convex, plus 1 minus alpha f tilde of x2. Correct. So as long as alpha is not equal to 0, the right hand side will always be equal to infinity. Correct. And anyway, if alpha equals 0 or equal to 1, the left hand side will always be equal to the right hand side for any function. Correct. Because if you set alpha equal to 1, then you get f of x1 on the left hand side, f of x1 on the right hand side. There's nothing to verify. And if alpha equal to 0, then you get f of x2 on the left hand side and f of x2 on the right hand side. So that's fine, right? So really the non-trivial part is when alpha is strictly between 0 and 1. But when alpha is strictly between 0 and 1, the right hand side would be alpha times f tilde of x1 plus 1 minus alpha f tilde of x2. x1 is not in the domain of f, so f tilde is equal to plus infinity by our definition of f tilde. Correct. So the right hand side is simply equal to infinity. So no matter what alpha x1 plus 1 minus alpha x2 is, it's always less than or equal to infinity anyhow. Right. So this condition is automatically satisfied for f tilde. If x1 and x2 are in the domain of f, then it becomes simple because f tilde of x1 equal to f of x1, f tilde of x2 equals f of x2. But now what happens to the left hand side? If x1 and x2 are both in the domain of f, can you always guarantee that alpha x1 plus 1 minus alpha x2 will be in the domain of f? Correct. So all of this will hold only if the domain of f is convex. So if the domain of f is convex, then f tilde will also be convex. So one fundamental assumption that we make is that the domain of f is convex. So as long as f is well defined, it's a convex function defined on some convex set, we can always consider the so-called extension, which will be convex throughout the entire space. But of course, at some values, it takes the value infinity. Correct. So this is defined so f tilde would be a function from V to the extended real numbers. So henceforth we will assume that f is defined over the entire V or entire Rn. Okay, and proceed from that. Now this is for a general f, right? Let's suppose that the function has a first derivative, that is a the gradient is well defined, and you can compute this for all possible x. So f from V to R and gradient f exists for all x. Okay, then f is convex if and only if the following conditions hold. So it's a necessary and sufficient condition. So for all x1 comma x2, we have f of x2 being greater than or equal to f of x1 plus the gradient of f evaluated at x1 transpose times x2 minus x1. Okay, so this is a necessary and sufficient condition for a sufficiently smooth function to be convex. Okay, this has a geometric interpretation. Now, what is the original geometric interpretation of a convex function? So, a function was convex if it looks like a bowl. So, according to the original definition, you take any 2 points, let's say x1. This is your x1. This is sorry. let us say this is x1 and this is x2. You take any convex combination, let's say alpha x1 plus 1 minus alpha x2. The function value always lies below. So the function is essentially below the straight line joining x1 and x2. Right? So the straight line joining f of x1 and x1 comma f of x1 and x2 comma f of x2 is kind of an upper bound for the actual function. Okay? So the curve lies below the line segment joining these 2 points. Only then is it convex. If this happens for every x1 and x2. Now what does this new statement say? Should be contained in what range? So that is always true, right? As long as the function is well defined. So the convex combination of f of x1 and f of x2 would basically be some point over here, right? So this quantity is defined for any function, right? You could always define this even if the function is not convex. Range of what? I don't quite follow.
Range of the area enclosed.
Again, I don't. So what do you mean by the area enclosed by the function? Here the function should act as a lower bound for this, right? I'm not quite sure what you mean. So in general, you could have some function like this, right? You take x1, you take, let's say, x2. So in this case, the convex combination will always lie in this range, right? Range between this and this, correct? So I'm not sure what you mean. You mean to say that if you look at the area above the curve, the region above the curve, then the line segment is basically any convex combination of these 2 points gives you something in this particular in this area, right? You're correct, and we'll come to that in a little bit. There's a specific definition for this particular set, right? The region enclosed by this curve. Okay, that's what we'll call the epigraph, and we'll see that the function is convex if and only if the epigraph is a convex set. But we'll come to that, so hold that thought for a little bit. Okay. Now coming back, so according to the original definition of a convex set, a convex function, the function is convex if this line segment lies above the curve, correct? Now let's try to analyze this new definition. So in R, so for functions over R, we get f of x2 should be greater than or equal to f of x1 times d by dx f of f evaluated at x1 times x2 minus x1. So if I fix a particular x1, okay, and I view the right hand side as a function of x, what kind of a function does the right hand side correspond to? It's a linear function. It's actually a straight line, correct? Because f of x1 is a constant. I'm fixing x1. x1 is a constant. This is also a constant, and it's only x2 that is allowed to vary. So this is a linear function of x2, and therefore the right hand side corresponds to a straight line, correct? Now What kind of a straight line is it? What is the slope of the straight line? Yeah, it's equal to the gradient, or the slope at x1. It's basically equal to the slope of the function at x1. And does it pass through x1 comma f of x1? It does, right? So what line does this correspond to, right hand side? Correct, but specifically for a given curve, it's the tangent, right? It's nothing but the tangent at x1. Correct. So this would correspond to the tangent. The right hand side is just the tangent passing through x1 comma f of x1, and that's true in any space. So this is a function on R, but over R2 this would just correspond to a tangent plane passing through x1 comma f of x1. All right. So what does this statement say? You take any point x2, f of x2 should be greater than or equal to the value of g of x2. So if I call the right hand side g of x2, right? So this is a straight line or a plane, it's a linear function. So this f of x2 is always greater than or equal to g of x2. So what this is basically saying is that no matter what point you take, so if you fix a particular x1 and consider the tangent at x1 passing through x1, then the curve lies strictly above the tangent. How?
That's a non-convex. But
Okay.
that it's over the time,
Okay.
then is that like a necessary?
It's a necessary and sufficient condition. It is also sufficient. Again, this should hold for every point x1. Right? So this should happen for every x1 and every x2.
Not even fixing x1, it should happen.
No. Yeah. So basically the tangent, so the curve should lie above the tangent for any point on the curve. Right? You take any point on the curve, you draw the tangent at that point, the curve will always lie above the tangent.
Say there exists a point in the convex set, is the whole set is lies on one side of the convex.
Correct. So that's also something that we'll see. So basically this region, so what would be the tangent at this particular point if I consider this to be a set, right? The tangent drawn at any point on the boundary is just the supporting hyperplane. Correct. So this entire set always lies on one side of the supporting hyperplane and is therefore convex. Okay. So it says that f is convex if and only if the function lies above the tangent to f at x1 for all x1. Consider any tangent to this particular function. The function value will, the actual curve for the function will always lie above this tangent. So that's the geometric interpretation of this particular condition. Now let's try to prove this condition. Okay, again there are two parts, there's a necessary part and a sufficient part. So first let's assume that the actual function is convex and the derivatives exist. Okay, our goal is to show that for every x1, x2, f of x2 is greater than or equal to the tangent. Right. So let's So how do we prove something like this? We know that f is convex, right? So consider some arbitrary x1 and x2. Okay, and let's consider a new point x equal to, let's say, 1 minus t times x1 plus t times x2. Just a convex combination of x1 and x2 for some t between 0 and 1. I can also write this as x1 plus t times x2 minus x1. Okay. Now, just by the definition of convexity, I have, so since f is convex, I have f of x to be less than or equal to alpha or 1 minus t times f of x1 plus t times f of x2. Or the right hand side is also equal to f of x1 minus t times f of x1 plus t times f of x2. So let's go back to what we want to prove. We want to show that f of x2 is greater than or equal to something, right? So let's keep the terms corresponding to f of x2 on one side, and everything, let's push everything else to the other side. There's only one term, t times f of x2. So I have t times f of x2 is greater than or equal to t times f of x1 plus f of x minus f of x1, or f of x2 is greater than or equal to f of x1 plus f of x. Let me write what x is. It is f of x1 plus t times x2 minus x1 minus f of x1 whole divided by t. Okay, so this is what I get just by using the definition of convexity and moving things around. Okay, just playing around simple algebra. Now can you guess what I should do in order to get the right hand side? I want to show that f of x2 is greater than or equal to f of x1 plus gradient of f times x2 minus x1. Correct. So one guess is we just take the limit as t tends to 0, right? So suppose that this is a univariate function. What would the right hand side be equal to? Correct. So if this were a univariate function, then I would simply get f of x2 greater than or equal to f of x1 plus f of x1 plus t times x2 minus x1 minus f of x1 divided by t times x2 minus x1 times, so if I'll just multiply and divide by x2 minus x1 right? I just multiply and divide by x2 minus x1 over here. But this is essentially equal to f of x1 plus f of x1 plus t times x2 minus x1 minus f of x1 divided by x1 plus t times x2 minus x1 minus x1, right? Exactly. So times x2 minus x1. So if I let t to tend to 0, this is true for all t between 0 and 1, correct? So as t tends to 0, this quantity tends to just d by dx of f, or right this way, this is just f dash of x1. Right, so then I would just get this. I just let t to tend to 0 and I get the derivative of f evaluated at x1 times x2 minus x1. But for functions in Rn, a higher dimensional space, I can't just multiply and divide by x2 minus x1. That's not allowed. But essentially the same thing holds. So let's go back to the definition of the gradient. How did we define the gradient? So the gradient was any vector which satisfied the following property. So the gradient satisfied the property that the limit as, let's say, y converges to x of f of y minus f of x plus gradient of f evaluated at x transpose y minus x whole divided by norm of y minus x. This is equal to 0. Okay, so no matter how you choose y, as long as y converges to x, the following holds. So if you're able to find some function gradient of f such that this satisfies, this is equal to the gradient. Okay. Now let's see what happens when I take y to be equal to what I had earlier, right? Which is x1 plus t times x2 minus x1. Take y equal to x1 plus t times x2 minus x1 and x to just be equal to x1. Then this would simply be equal to limit t tending to 0, because as t tends to 0, y tends to x, f of y minus f of x plus gradient of f transpose. What is y minus x equal to? T times x2 minus x1. So this would just be t times x2 minus x1 divided by t times norm of x2 minus x1. I think I made a small typo here. It should be minus here and here. Okay, so let me say that this quantity is the vector in the numerator is some e of t. That's sort of the error vector, the error between this quantity and this quantity. E of t to be equal to f of y minus f of x minus the gradient of f transpose t times x2 minus x1. So this is basically saying that the norm of e of t divided by t times x2 minus x1 converges to 0 as t tends to 0. So I can write f of y minus f of x divided by t to be equal to e of t divided by t times e of t plus gradient of f of x transpose x2 minus x1. Right, so f of y minus f of x is equal to e of t plus this particular quantity. I divide both sides by t and I get this particular quantity. Right, and what I know is that e of t is a vector whose norm tends to 0 as t tends to 0. In fact, the norm of e of t by t tends to 0 as t tends to 0. Correct? You agree with me? So let's go back to what we had here. What we had over here. Right? Let me call this equation 1. Let me call this equation 2. So this particular quantity would just be equal to e of t by t plus gradient of f times x2 minus x1. So f of x2 greater than or equal to f of x1 plus E of t by t plus gradient f of x1 transpose x2 minus x1. Now I just let t to tend to 0, right? Since the norm of E of t by t tends to 0, x2 and x1 are fixed, right? The only thing I'm varying is t. So as I let e to tend to 0, the norm of E of t by t tends to 0. So every component of E of t should also tend to 0. Right? Every component of E of t by t should also tend to 0. As t tends to 0, E of t by t also tends to the 0 vector. So f of x2, and this particular statement is true for all t between 0 and 1. So no matter how close t is to 0, the statement still holds. So f of x2 is greater than or equal to f of x1 plus gradient of f evaluated at x1 transpose x2 minus x1. Any questions? So this proves one half of the statement. Now we need to show that if this statement holds, if this holds for all x1, x2, then the function f is indeed convex. All right, and that is a slightly easier thing to do. So you consider an f such that for all x1, x2, f of x2 is always greater than or equal to f of x1 plus gradient of f at x1 transpose x2 minus x1, right? So the function always lies above the tangent. So if for a function the tangent always is a lower bound on the true function at every point, then we want to show that f is indeed convex. Now fix any x1, x2, and let's take an alpha between 0 and 1. Okay, we want to show that this satisfies the original definition of convexity, that f of alpha x1 plus 1 minus alpha x2 is less than or equal to alpha f of x1 plus 1 minus alpha f of x2. So let's consider, let's define x to be equal to alpha x1 plus 1 minus alpha x2. Now I'll basically just apply this for both for x1 comma x and x2 comma x. This is true for all x1, x2, right? So in particular, this is also true if I take f of x1 greater than or equal to f of x plus gradient f of x1 gradient f of x transpose x1 minus x, and f of x2 is greater than or equal to f of x plus gradient f of x transpose x2 minus x. So let me call this 3. So, and let's just take alpha times equation 4 plus 1 minus alpha times equation 5. So I get alpha times f of x1 plus 1 minus alpha times f of x2 greater than or equal to alpha f of x plus 1 minus alpha f of x, that's just f of x, plus gradient f of x transpose times alpha x1 plus 1 minus alpha x2 minus alpha x plus 1 minus alpha x, which is just x. But what is x equal to? Alpha x plus alpha x1 plus 1 minus alpha x2. If I substitute that here, this quantity is just equal to 0. So this is equal to 0. And this, so all that remains is f of x, which is equal to f of alpha x1 plus 1 minus alpha x2. Right. So f is convex. So if you think about this, these two notions of convexity, right, or these two definitions of convexity, essentially what they're saying is that you take any convex function, you'll always have sort of two lines, one which gives a lower bound on the function and the other which gives an upper bound on the function. So any straight line joining 2 points on the curve will give you an upper bound on the function, but the tangent at any point will always give you a lower bound on this function. So that's sort of the geometric interpretation behind this. So I'm talking about this line, right? It gives the upper bound, of course, for only a specific interval, not everywhere. But the tangent gives a lower bound for the entire function. So in some sense, this is more powerful. There's another useful property of convex functions, one that in many cases helps you to prove convexity of various functions. So suppose f is some function defined on some arbitrary vector space, let's say Rn. Right? Let us define g of t for any x1, x2 and t. Let's define g of t to be equal to f of x1 plus t times x2 minus x1. Alright, so this is just the straight line passing through x1. In fact, the straight line passing through x2 and x1, right, as you vary t. Now we can show that f is convex if and only if g is convex for all x1 and x2. Now this does not require any additional properties on f. It need not be differentiable or twice differentiable. Okay, so for any convex function f, if g is convex for all x1 comma x2, then f is also convex, and vice versa. So what is the interpretation behind f, behind this particular statement? So you take, yeah, I'm sorry. Sure, there is that. So right now I'm assuming that f is defined everywhere. Okay. So what is x1 plus t times x2 minus x1? This is not particularly helpful for functions on R, right? It's only helpful for higher dimensional functions. So you take any 2 points, basically you're considering the straight line passing through those 2 points. And if you think about it, this particular quantity f of x1 plus t times x2 minus x1 is like essentially taking a slice, right? So you can think of f as some function which looks like a bowl, right? Or any function, it's some kind of a surface, correct? So you take a cut on this particular surface, cut that is perpendicular to the horizontal plane, right? And you look at the intersection of this cut along the function, right? Okay, so if you try to visualize it, so that basically gives you a curve, correct? So you could have some kind of a surface that looks, let's say, like this, right? So you should think of this as a 3-dimensional surface, and you just cut through the surface, right? You take a plane that basically cuts through this. Now along this plane, the intersection of this plane and the function and the surface, you get some kind of a curve, right? The point is that no matter how you choose this particular plane, this curve will always be convex. So you look at the function along any particular line, the function is guaranteed to be convex. Okay, does that make sense? Okay, and if this happens for every single direction or every single plane, that every single cut that you take, then the function is guaranteed to be convex. Which one?
You take R.
Which one? So this, I'm assuming there is a function on R square, right? That would be a surface. When you take a plane and cut through it, right? So you're looking at it through one particular direction. You get the intersection of this plane, take any plane, and take the intersection of this plane with the surface, correct? You will get a curve, right? A one-dimensional curve. What this is saying is that if the original surface is convex, then the curve that you get will be convex. Okay. So you always consider a plane that is perpendicular to the horizontal plane, right? You take any vertical plane, right? Suppose that this is your function looks something like this. This is your surface. You take a vertical plane in any direction and you cut through this particular plane, right? So now take the intersection of this plane and this curve. It's as though you're looking, it's a 3D surface, but you're looking at a 2D representation of this. So you'll get some sort of a curve. Now if this curve this one-dimensional curve that you get is a convex function, no matter how you choose this particular plane, no matter how you orient the plane, you will always get a convex curve, a one-dimensional convex curve, then the original surface is convex.
Direction, if you get the convex intersection
Correct.
in the whole function, which we are getting intersections is convex.
Correct. Yes. Okay. Any questions? So in some sense, this is a zeroth order condition for convexity. What we saw previously, if the function has a derivative, then and we have f of x2 greater than or equal to whatever f of x1 plus gradient times x2 minus x1, then that's what is called a first order condition for convexity. We also have a second order characterization, second order condition for convexity. So if f from Rn to R, and let's say that the Hessian exists, right? Then f is convex if and only if the Hessian evaluated at any point is PSD for all x. Right? So I will not prove these two statements, this particular condition. Now it's fairly easy to prove this. You just need to use the definition of convexity repeatedly. Basically, to prove that f is convex, to prove that, suppose you start with f being convex and you want to prove that g is convex, you just take alpha t1 plus 1 minus alpha t2 and rewrite the terms in here to get g of t1 plus 1 minus alpha times g of t1 plus 1 minus alpha g times g of t2. So I try to represent it in that particular form. That's fairly straightforward. In order to prove that f is convex if g is convex, again you use something very similar. You take two sets of points and then try to use this property that alpha times g of t1 plus 1 minus alpha times g of t2 is always greater than or equal to g of alpha t1 plus 1 minus alpha t2. So that's not too hard to prove. The proof of the second order characterization requires a little more thought, but it is very similar to what we did in the one-dimensional case. If you go back to your notes about how we proved that a function is convex if and only if the second derivative is always greater than or equal to 0, it's again very similar. You effectively that we want to show that this quantity is PSD, or in other words, x transpose times this times, or let's say y transpose times this times y is greater than or equal to 0. Okay, so you try to express this Hessian in terms of the gradients, correct? And again, you keep trying to think about how you proved it in the one-dimensional case. So function is convex if the derivative keeps increasing, right? And you can interpret this first order condition as something similar. Of course, it doesn't really say that the gradient keeps increasing, but you use something similar to this. The tangent is always a lower bound for the true value of the function. So you express the Hessian in terms of the gradients and then try to use these properties, the first order and the zeroth order conditions. Okay. Any questions? Okay, so let's have a quick quiz.